Hi, I'm Bennett. In this video, I want to talk to you about the basics of testing in a software project and how they play out in practice. I would also like to introduce you to a risk-based approach to testing. Testing is the process of planning, preparing, and measuring with the aim of determining the characteristics of an IT system and showing the difference between the actual and the required state. This somewhat unwieldy definition by Pohl, Kuhlmann, and Spillner points to the central task of testing, namely the comparison of the actual state with the required state. This definition does not say that a test must always be carried out against a hard specification of any kind, but it deliberately speaks softly of the required state, against which the actual state is to be tested. There are several reasons for this. On the one hand, software systems are typically not created to meet a specification, but to fulfill a specific task. It is possible that the system defined in the specification does not solve the task at all, or it may not solve it completely, efficiently, or in a user-unfriendly way. Recognizing such deficits can also be the task of the test. Approaches to this are explained in more detail in the video on manual testing. However, the required state from the definition can also be interpreted in a completely different direction. Not all details of a specification are equally important, so that the software can fulfill the task assigned to it. Some things must function exactly as specified, while minor deviations or errors may be tolerable in other parts. Testing, therefore, does not have to test everything with the same intensity, but should concentrate on what is necessary to ensure that the software can reliably perform the task assigned to it at the required quality level. Finding the right balance between effort and return for the specific project, i.e. test coverage and residual risk, and maintaining it throughout the software's lifecycle is the central challenge in testing. There is no patent remedy for this, but there are a few guiding principles and implementation practices. These will be the subject of the following videos on the testing module. I will come back to one very helpful guiding principle at the end of this video, and that is the risk-based testing approach. But first, a few basic considerations. Formally proving the correctness of software through testing is impossible for all but the most trivial problems. A brief consideration should make this clear. Suppose you could prove the correctness of a program by means of complete path coverage. Path coverage means that every possible path through the source code has been run through once and the result checked. In the example shown here, the number of paths and therefore the number of test cases required grows exponentially with the number of branches in the program flow. It may still be possible to achieve path coverage for individual classes or simple algorithms, but if you consider a software system as a whole, this is practically impossible. Because in practice, it is never possible to try out all theoretically possible inputs and flow paths. You have to limit yourself to a set of selected examples. These should allow the best possible conclusion as to whether the program as a whole is likely to behave correctly. Test design procedures are one approach to finding the smallest possible, yet representative set of input data or test cases. The consideration also points to another possibility for reducing the test effort. If it is possible to split the software into as far as possible independent parts, the exponential growth per branch only applies within each of these parts, while the test effort for the overall system, depending on the degree of decoupling, is at best the sum, at worst the product of the efforts of the individual parts. A good software architecture and a clean design, which minimizes the dependencies and interfaces between the individual components, also minimizes the required testing effort. In this case, each component can initially be considered in isolation, and only the interaction of the components via their interfaces needs to be focused on in subsequent test stages. This divide and conquer principle is one reason for the efficiency of the test pyramid, which I would like to discuss briefly below. The test pyramid is a model for designing a test automation strategy, i.e., the question of how to use automated tests in a project. Unit and component tests form the basis and foundation of the test pyramid. They are typically created by the developers during development and cover the functionality of the developed classes and methods in detail. The next level is the automated tests at API level, which test the external interfaces of the fully integrated application core. A large part of the technicality presented on interfaces can already be tested very efficiently at this level, which is why it is well suited for automated acceptance tests. The third and final stage of test automation is GUI testing, which is based directly on the user interface and controls it with suitable tools. Automated tests from the GUI are complex and demanding if they are to be robust and maintainable. They also require a relatively long runtime during execution. The test suite should therefore remain manageable and be limited to aspects that cannot be tested otherwise or only cover the customer's most critical use cases. Above the automated tests, there are always manual tests that cover everything that cannot be tested by machine. This includes, for example, acceptance tests by the end user, usability tests, or cross-system tests. In summary, the test pyramid shows that the focus of test automation should be on the unit and API level. Test-driven development and other approaches for development accompanying tests help to generate the required broad basis of unit tests and at the same time support the development process. The test pyramid was proposed by Mike Cohn in 2009, originally to structure test automation in agile projects. At its core, it is based on the idea that locally testable functionality should also be tested locally, and that higher test levels should focus on the integration, i.e., the interaction of locally tested functional units. As this divide and conquer principle is fairly universally applicable, the test pyramid is also used in other contexts to visualize test approaches, but now back to our basic thoughts on the test. We saw earlier that even the most thorough test cannot prove the correctness of software, but can at best give a credible indication. This insight may be somewhat depressing at first. However, it leads to two very relevant practical insights. Testing can only ever prove the presence of errors, not their absence. A green test suite, therefore, does not mean that the tested program behaves correctly, but only that the test has not uncovered any errors. This is because a green test suite can have two causes. Either the software is of such good quality that it does not contain any relevant errors, or the test suite is of such poor quality that it does not uncover any errors that may be present. When evaluating a test result, you have to be able to distinguish between the two causes, and this leads to the finding. In order to be able to draw conclusions from the green test suite to the probable correctness of the program, an understanding of the quality of the test is required, specifically, how well the test actually covers the required capabilities of the software. This requires a structured test procedure that defines and justifies which parts are tested, how intensively, and in what way. The test procedure should be appropriately documented in the test concept. A structured test procedure does not necessarily mean testing every edge case or error scenario just because a test design procedure has revealed it. A structured approach is much more about recognizing when gaps in test coverage are found and then making a reasoned and conscious decision to either close the gap or leave it open. The decision should be guided by risk and efficiency. The risk-based test approach helps here. The risk-based test approach is based on the fact that risk minimization is a central test objective. Only the risks associated with quality deficits in the software are considered. Risk is defined as the loss caused by an error in production multiplied by the probability that this error will occur in production, and the whole summed up over all conceivable errors. The loss caused by an error cannot usually be influenced, but is defined by the problem, i.e., the project object and the context. What can be influenced by the test is the likelihood that errors remain undetected until production and thus cause loss. The more intensively we test at a certain point, the more we reduce the probability of a fault remaining undetected. This risk formula will never be calculated with analytical precision, but important guidelines or instructions for action can be derived from it. As a project manager or client who has to decide on the test budget for a project, the formula means that different projects have different test requirements in order to achieve the same level of risk. For projects with a higher potential for loss, you need to invest more testing effort to reduce the likelihood of a bug going undetected. Above all, in these cases, you will have to invest considerably more test documentation effort in order to be able to draw the conclusion that a green test suite means a low probability of errors. As a test manager, consideration helps to find the right test focus. The risk-based guideline is here. Test most intensively where the risk is highest, i.e. the product of the amount of loss times the probability of error. This means focus on the topics where the loss potential is highest, but also test intensively where you suspect that errors occur frequently, i.e. where there is a high likelihood of occurrence. But the approach is also helpful as a developer or tester to prioritize different testable aspects against each other. Here too, the two questions, what loss would be caused if a detail to be tested had been implemented incorrectly, and how sure can I be that the detail has been implemented correctly, help to decide whether or how intensively to test an aspect. Two examples illustrate the application of the risk-based testing approach. The first example is about defining the test strategy for a medium-sized development project. The task was to define the test priorities and allocate the available test budget accordingly. The approach for test automation was also to be determined. In technical terms, the project involved the creation of a system for the automated valuation of securities portfolios at a bank. Using a complex set of rules, the system evaluates the probability of securities in the portfolios defaulting, i.e., not being repaid. The project had already failed once in the past and was stopped. The reason for the failure was the complex dependencies within the set of rules. They mean that if you change the rules in one place, other rules that have already been implemented no longer apply or behave differently. When defining the test strategy, a look into the past alone means that the set of rules must be the central focus of the test. However, if a risk-based test approach had been used, the predecessor project would also have had to come to this conclusion without knowledge of the history, because a portfolio evaluation system that calculates incorrect evaluations causes maximum loss. The level of loss caused by errors in the set of rules is therefore very high. Because the dependencies make the rules complex and error-prone, there is also a high likelihood that errors are lurking here. To reduce the risks, test automation was implemented that not only checks the implemented rules in isolation, but also always in conjunction with all other rules already implemented. The automation was based on sample portfolios for which the specialist department manually calculated the expected valuation results. Each time a rule was changed, all sample portfolios were automatically checked. This meant that unwanted side effects could be identified immediately and clarified with the specialist departments. However, focusing the test strategy on the set of rules also has its price. Less test budget was left for other areas of the application. For example, the development team only carried out rudimentary testing of the interfaces with which users can search for and display the evaluation results. The reason for this was that although errors in the GUI hinder the work of the users, and therefore have a noticeable potential for loss, such errors are comparatively easy to detect in an acceptance test. It was therefore agreed with the specialist departments that they would pay particular attention to the user interface in their manual acceptance tests, while they would not have to check the displayed evaluations in detail, but could rely on the automated tests of the rule set. Such a division of labor has proven itself in this specific project context, but this will certainly not apply to any project context. The great strength of the risk-based approach always comes into play when things need to be weighed up against each other and ranked in order of importance. These can be, as in the previous example, entire functional units or individual test ideas or test cases. Quality criteria such as usability, security, and performance can also be prioritized against each other based on risk, e.g., in order to decide which quality criteria should be backed up with tests and how intensively. The second example was about evaluating test ideas for a manual test. Manual tests are characterized by the fact that writing a test is comparatively quick, especially if you limit yourself to the aspect to be tested when writing it down, while the detailing and execution of a manual test takes a relatively long time. It can therefore happen that you have to decide which tests you want to carry out in any case, and which are for the reserve bank if there is still time left at the end. For the selection, it has proven useful to first systematically determine all test cases according to the test case identification methodology, and to note them as an aspect at heading level. The test cases can then be prioritized based on risk and, depending on the framework conditions, only some of them can be detailed and implemented. The advantage of this approach is that any necessary decision to leave test aspects untested can be made consciously, giving a better assessment of the quality of the test suite. I hope I was able to give you some new insights into the invariance of testing and convince you that a risk-based approach can be a universally usable guiding star in testing. Have fun with the other videos and see you soon.